Got it? I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for calculus. Thank you for these students. Just pray that you would just help us use this time wisely, Lord. And we thank you for the weekend that's just about to start, Lord. In your name I pray. Amen. Okay, so I will take questions about homework after I get through just a couple things here. First of all, surface area. Another application of the infinitesimal method. So the kind of surface areas we can consider, basically we're only thinking about one kind of boring case. Something like this. So what I'm thinking about is something like y equals f of x for the graph, all right? And if you can imagine that, rotated, right? You can imagine rotating that around the x-axis, right? So if you take a graph, right, and you rotate it around the, sorry, I'll stay over here, and you rotate it around the x-axis, then what do you get? You get like a surface, right? Simple example, you know, if I took a line, right, and I rotated it around the x-axis, what would that get me? Just a line segment, actually. You'd get like one of these guys, right? Like a partial cone. So we're interested in how would you calculate the surface area of something that was kind of curved like that? So the answer is basically to chop it up into little ribbons. All right, so you chop it up into these like little ribbons, and so the question is, what's the area, or in this case, surface area, really, of a particular little ribbon, you know? So, I'll do it again down here. So the way to do it, essentially, is to say, okay, so that's the radius. The radius is exactly y, right? But y is equal to f of x in this case. And this distance along here is what? That's ds. That's a little bit of arc length that's subtended along the surface, right? So the area, the little bit of area, would be just f of x times ds. All right? So okay, we can clean this up a little bit, right? Like yesterday, we learned that we can write ds, the infinitesimal arc length for a graph, as what? We worked this out yesterday. It's really the square root of 1 plus df dx, quantity squared dx. Okay, so there you have it. That's our infinitesimal area from this little ribbon. And if this shape is going from x equals to a over here to x equals to b, if you want to find the total surface area, you just look at the integral from a to b of f of x times the square root of 1 plus df dx squared dx. And that will give you the surface area. Yep.
I thought that it's supposed to be 2 pi x, that we take the surface area of a...
Oh, right. I'm sorry. You're absolutely right, because he's like, well, if you unwrap this, wouldn't it be something like... Yes. I'm sorry. Exactly right. I'm missing a 2 pi here, right? Thank you. I knew something felt wrong. It would have become glaringly obvious for me after I tried to work out the next example and got something unfamiliar. So, yeah, that 2 pi is important. And it's there for essentially the same reason as it was there in the method of cylindrical shells yesterday. So the idea basically is if you take this ribbon and you just cut it, right, and you lay it out flat, something like that. This, well, you could take this, right, and put it over here, and then this distance would be 2 pi f of x, and this height would be ds.
So it's 2 pi. So 2 pi r is circumference.
2 pi r is the circumference, yeah. So I mean, that's essentially the distance around this is 2 pi r, and then ds gives you the thickness. Now, if this is not convincing to you, I mean, that's fine. There's a more careful proof in the book in terms of chopping the surface up into a bunch of little ribbons and doing explicit calculations with cones and such. What's that?
But for volume, we need the area times the depth, so we like 2 pi r squared.
No, we're not doing volume. We're asking a surface area. Yeah, it's okay. You're worrying me for a second there, but how about this? Let's take this graph, y equals the square root of r squared minus x squared for minus r less than or equal to x less than or equal to r. Let's rotate this thing around the x-axis and let's find the surface area of this guy. Okay, so we calculate. Surface area, integral from minus r to r. I'm supposed to do what? 2 pi. F of x in this case is the square root of r squared minus x squared. All right. And then I'm supposed to multiply that. Blip, 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 blip. Multiply that by, ay caramba. I regret my life. What have I done? 1 plus df dx. So this is my f of x in this case, all right? What's df dx? I suppose it's minus 2x over the square root of 2 times the square root of r squared minus x squared by the chain rule. 2's cancel. So, you know, I'm working off this boxed formula over here. Right now, I'm trying to wrap my mind around what's df dx quantity squared. I'll just write it in here. Minus 2x over, let me cancel the 2's here. So I've got minus x over the square root of r squared minus x squared, quantity squared. And I think I still owe us a dx. I'll bring the 2 pi out front because it's harmless. And honestly, this is clearly an even expression, right? If you replace x with minus x, you get the same thing. So let me just go ahead and cut our suffering and say integrate from 0 to r. But if I do that, I have to double it. Okay? Using the even integral trick. And, you know, the square root of a times the square root of b is equal to the square root of ab, right? So I can multiply this in there, and I'm really left with the integral of r squared minus x squared times what? Times 1 plus x squared over r squared minus x squared. The minus goes away when you square the df dx term. You guys with me?
Where did that 4 come from?
Notice I changed the integral from minus r to r just to 0 to r. So I'm just using the symmetry of the problem to double it from 0 to r. 0 to r would be easier calculation. And now you multiply, right? So we got what? We got 4 pi integral from 0 to r. Square root looks like r squared minus x squared plus x squared. Ah, cool. Which is what? Man, I thought we were going to have a chance to do some integration in here. This is shaping up to be rather boring. This simplifies to r. R is positive here, right? So I can pull it out. Goodness gracious. Well, this is so embarrassing. This is too easy. All right, 4 pi r squared then. Here, I'll write down some work to make it seem like I actually did something more here. Incidentally, as a method to remember this, remember we worked out that the volume of a sphere was 4/3 pi r cubed the other day? Did we do that? Did I do that? Oh, man. Huh. Yeah. Oh, well. I did that? I can't remember.
We did pyramids.
Oh. Well, anyway, some of you know this, right? Fun fact, if you differentiate this, this is dv dr, isn't it? So like the derivative of that with respect to r is the surface area. Just like, by the way, if you take the derivative with respect to r pi r squared, what do you get? You get the circumference. This doesn't work for other shapes. There's something really special about spheres and higher spheres. I mean circle's a sphere. Yeah, hyperspheres. Although, I mean, another way to look at this is if you can remember one of these correctly, you can always get the other, right? Okay, there's an example of surface area for you. I don't think I really expect you to memorize that formula at this point in your life. So if this did come up on the test, I would remind you the formula for surface area, okay? I do expect you to remember an inordinate number of details about cosh and sinh and sine and cosine, though. So don't misunderstand my friendliness. Let's see here. Okay, so next example is physics, work. So you guys know, or maybe you don't, I don't know, work, we're all taught this, is force times distance. I mean, I'd like to say we're all taught this. Maybe you've been taught this in like a 4th or 5th grade science class, maybe, I don't know, 6th grade, something like that. Somewhere in middle school. This is the first thing you should be taught. Work is force times distance. So that's really very, I mean, so basically you're thinking you've got some box, there's some force of friction or whatever. Anyway, suppose you put 10 newtons on it and you go 30 meters, right? What's the work done by this force over that 30 meters? The work is 10 newtons times 30 meters, 300 newton meters, aka 300 joules. There you go, work done. Now this assumes something though. Here we assume a couple things. Number one, the force is directly in the direction of the motion. All right. And the other thing we're assuming here is that the force applied is constant over the motion. All right? Now, both of those assumptions are unrealistic for many interesting physical processes, right? You might apply the force in different directions, or you might apply the force so it's not aligned with the direction of the motion at various points and so forth. Now, I just picked up a black marker. Sorry. I was going to try to do some contrasting. Anyway, sorry. It's my own stupidity. So this, I can't fix that in here. To generalize it being in a different direction and stuff, to take care of directionality of the force, you need the dot product. So the next generalization of this is work is equal to the force dot the displacement. Or that's the next sophistication here. The force is constant over the motion. Well, that I'm going to talk about. We'll talk about this shortly. So we can do work. We're going to learn is the integral from a to b of f of x dx. You put both of these together, you get the real story, which is that the work is equal to the integral, line integral, over a curve of f dot dr. So this is really what you want for all situations, but the line integral is part of Calc 3. Okay? So this is just the start of the story. It's not the end of it. If you were taking physics with me, I would teach you that in Physics 1, which is why Calc 3 should be a prerequisite for Physics 1, among other things. It's not. Okay, so we've decided then we're going to focus our attention on one-dimensional motion, and we've got a force. Here's force of x1, and then over here we have got a different force applied, the force of x2. So like the point is f of x1 is not necessarily equal to f of x2. So the force varies. This is the problem. And so what I want to say is, suppose you have a force that's pushing on something, all right? It's pushing directly in the direction of motion, all right? And our convention is in the motion, direction of motion is positive, opposite the direction of motion is negative. It's one-dimensional problem. And we're going from x equals to a to x equals to b. The question is how much work is done by this variable force, all right? Do you guys understand the problem? What's the net work done by a variable force going from x equals to a to x equals to b? This is again a problem we can solve with the infinitesimal method. Let me explain to you how. What you imagine is just a little bitty tiny displacement like this. So suppose you're going over here. You've just moved just a little bit. So now this is at x1 plus dx, all right? So let's say this one's at x, that one's at x plus dx. What's the little bit of work done in that displacement? Well, there you could say it's f of x. That's the force at that x, right? And times the distance, which is just dx. This makes sense because the force does not jump. It's, the force can vary over a finite distance, right? But if you just focus your attention on one little infinitesimal displacement, the force is constant. And that's the idea. And then so to find the network, we just add them up, which is an integral. Integrate from a to b, f of x dx, and there you go. That's the formula for work in one dimension. You just integrate the force. Simple as that. Show you an example. Pretty famous example. You got a spring, right? It's tugging on some mass m. We don't really care what the mass is. The spring force, what's the spring force? Spring has constant k. Say this is x, right? So F, actually it's not x. I mean, technically it's x naught plus x, where x is the, x should be the distance from the equilibrium. So let me label it a little bit differently. So let's suppose that if the mass is like at equilibrium, that's like here. So that would be x equals to 0. But then if it's stretched out, I saw there was a question, just a second, I will be with you. Over here, stretched out a little bit, right? Then that's x greater than 0. I don't want to get the picture too cluttered, but if x is less than 0, it means the spring is compressed, right? So you put all that together. Hooke's law says F is equal to minus kx, where x is the distance from the equilibrium position for the system. So if it's positive, the force is negative, which means it's pulling it to the left, right? If the spring is compressed, then x is negative, so the force is positive because the spring is pushing the mass back the other way. So we can calculate what's the work done if the spring goes from, say, x equals to a to x equals to b. It's just that, right? So and there you have it, 1/2 k minus 1/2 kb squared plus 1/2 ka squared. I mean, I could clean it up, but there it is. That would be the work done. Anyway, I asked you a token one of these on your quiz that I'm going to give you in a second or two. You have a take-home quiz due next Monday. Our test is when? Tuesday. So the take-home quiz is not just about the material we've covered the last week. In fact, it's just maybe like 20% of what I'm giving you. It's a lot of it's review of the other weeks. Okay. So in some sense, quiz 4 is, I wouldn't say it's a practice test, but it will help you practice for the test. That is true. You can work together on quiz 4. I don't like to punish the honest people, so I just say you guys can work together. However, you should not copy answers or copy steps. If when the grader grades these, he finds 2 of them that look very similar, he has instructions from me to take the points and divide them amongst the 2 people that had turned in the same assignment. So if 3 people work the same thing and you get 100, everyone gets a 33. 0.3, 3, 3, 3, 3. So don't do that. Also, I added this. I'm giving you, you can work on your own paper, all right? But with this privilege comes a certain responsibility, which is that the problems must be done in order, right? And let's say you have problems 1, 2, 3, and then the next problem goes to number 5. So I know the game. I was a student. I understand the game. I know what the game is. The game is grader doesn't see number 4 is missing. So if I can't figure it out, if I just stack it in there, maybe he'll miss it and I won't get, even though I don't know how to do it, if I just, kind of do that. Anyway, this is a game students like to play in take-home stuff. And so, here's the rule. If you're missing a number and you don't include a number saying, I haven't done this, or missing, then you lose double the points on that one. Just so you know.
Wait, what?
So if your solution has 1, 2, 3, and then you go to 5, there's no mention that number 4 is missing, you lose double the points on number 4. So what am I encouraging you to do? Write number 4 there, but more importantly, put your problems in order as a matter of common human decency towards the grader. Which is not me, by the way. I'm just, so. These are not points any of you are going to miss now that I have told you this, right? I mean, anyway. So, it's fine. All right. Well, hey, guys, that's all I've got for applications in here. As far as the ones I would actually ask you on the test, I would stick to area, volume, just area and volume. I don't think I'd even test you on arc length just yet. We'll cover arc length on tests later. There's a problem or 2 in the quiz that you can do, but I think that's area and volume is quite enough for the test. So, any questions then about the homework or anything?
So you said we can work the quiz together, but if we get the same answer, we put points in the bottom?
I said if you copy, how would we know that you copied answers? Like suppose you have the same weird wrong answer. Would be a way we could figure it out, for example. My point is, it's fine for you to work together. You can talk to each other about it, but do not copy each other's work. This is not complicated, right? Does this make sense? Yeah?
This stuff is on the test. Or you just said like there was like one more question.
Oh, thank you for that. I should clarify. That also might be on the test, the force. But if I ask you to calculate the work done by a force, I'm just saying to do this integral, so it's really not that exciting. This is far less complicated than my area or volume problem. But thank you. Any other questions about what's on the test? I'm not.
What are the answers?
What are the answers? I don't know. I'd have to have written the test. Let's see here. What's that? Can you use your... Yeah, I mean, you can...